November 19th, 1943, Dobodura Airfield, New Guinea. The tropical sun beat down mercilessly as Captain Akira Yamamoto of the Imperial Japanese Army Air Force stood before the most unusual prize his unit had yet recovered. The aircraft before him was enormous, its twin booms stretching like metallic wings of some mechanical dragonfly, each housing a massive Allison engine that gleamed even through the coating of jungle mud and battle scars. This was the Lockheed P-38 Lightning, the American twin-engine fighter that had been terrorizing Japanese forces across the Southwest Pacific for nearly 2 years, and for the first time, the Japanese had won largely intact. What Yamamoto and his team of technical specialists were about to discover would fundamentally alter their understanding of American aviation capabilities. The examination would reveal not just an aircraft, but evidence of an industrial philosophy so alien to Japanese thinking that it bordered on the incomprehensible. The Lightning had been forced down 3 days earlier after a fierce dogfight over the Huon Gulf. Second Lieutenant Robert Forot of the 49th Fighter Group had been attacking a formation of Betty bombers when Japanese Zeros caught him by surprise. Multiple hits to one engine and severe damage to the port boom forced an emergency landing on what Forot believed was Allied-controlled territory. It was not. Japanese ground forces captured him within hours, and the P-38, though damaged, was far more intact than any previous example they had recovered. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The recovery operation itself demonstrated Japanese determination to acquire American technology. Engineers from the 4th Air Army's Technical Intelligence Section arrived within 12 hours. Despite Allied air superiority and the constant threat of strafing attacks, they worked for 2 full days dismantling components, documenting the aircraft, and preparing it for transport to Wewak, where better facilities existed for detailed examination. The effort required was extraordinary. The P-38, even damaged, weighed over 15,000 pounds. Moving it through jungle terrain without proper equipment meant organizing hundreds of laborers. Components too large to transport were measured, photographed, and documented in situ. The massive propellers, each 11.5 feet in diameter, were carefully removed and crated. Engines were drained of fluids and prepared for shipment. The cockpit was emptied of every instrument, switch, and control, each item catalogued for later study. Captain Yamamoto, who had shot down 6 Allied aircraft and held a degree in mechanical engineering from Tokyo Imperial University, led the technical assessment team. His credentials made him ideal for this assignment. He understood both the pilot's perspective and the engineering principles underlying aircraft design. His preliminary report, written at the crash site and discovered in Japanese archives after the war, betrays both professional admiration and growing concern about the implications of what he was seeing. The aircraft is of a size and complexity unprecedented in our experience with single-seat fighters. The twin-engine configuration, while theoretically understood, has been executed with engineering sophistication that suggests manufacturing capabilities far exceeding our current estimates of American industrial capacity. Preliminary examination indicates precision in component manufacture and system integration that will require thorough analysis to fully comprehend. To understand what shocked Japanese pilots and engineers about the P-38, one must first understand the context of Japanese aviation development and the strategic situation facing Japan in late 1943. The war was not yet obviously lost, but the tide had definitively turned. Guadalcanal had fallen in February. The Bismarck Sea disaster in March had demonstrated devastating Allied air superiority. Yamamoto Isoroku, architect of Pearl Harbor, had been killed in April when P-38 seconds ambushed his transport, a psychological blow that reverberated through the entire Japanese military. Japanese fighter design philosophy had evolved from different priorities than American thinking. The Zero, Japan's most famous fighter, embodied a belief in maneuverability above all else. Lightweight, excellent turn radius, long range, these were the characteristics Japanese designers pursued, accepting minimal armor protection and light armament as necessary trade-offs. This philosophy had worked brilliantly in 1941 and 1942, when Japanese pilots with superior training could exploit the Zero's agility to defeat heavier, less maneuverable Allied fighters. But by 1943, the equation had changed. American pilots had learned not to dogfight with Zeros, but to use superior speed and firepower in hit-and-run attacks. More critically, new American fighters like the P-38, F-4U Corsair, and F-6F Hellcat possessed both performance advantages and the structural strength to absorb battle damage that would destroy a Zero. Japanese aviation was confronting a fundamental truth. Their design philosophy, optimized for a short victorious war, was inadequate for the grinding attrition of prolonged conflict. The P-38 Lightning represented everything Japanese aviation was not. Where Japanese fighters were small and light, the Lightning was massive and heavy. Where Japanese fighters sacrificed protection for agility, the Lightning incorporated armor and redundancy. Where Japanese fighters had single engines of modest power, the Lightning had two engines producing a combined 2,950 horsepower. The contrast could not have been more stark. The P-38's origins dated to 1937, when the United States Army Air Corps issued a specification for a high-altitude interceptor capable of reaching 20,000 feet in 6 minutes and achieving speeds of 360 miles per hour at that altitude. This specification alone exceeded what most existing fighters could achieve. Lockheed's response, designed by Hall Hibbard and Kelly Johnson, was revolutionary. Rather than trying to coax such performance from a single engine, they opted for two engines. This decision drove every other aspect of the design. The twin-boom configuration emerged as the optimal solution to the two-engine requirement. Placing engines in the wings where drag was minimal created a need to position the tail surfaces somewhere. Rather than a conventional single tail, which would require a long, heavy fuselage boom, Lockheed's designers created twin booms extending from each engine nacelle. This distributed structural loads efficiently and provided ample internal volume for fuel, armament, and systems. The central nacelle, positioned between the engine booms, housed the cockpit and the aircraft's devastating armament. 4 50-caliber machine guns and one 20mm cannon, all mounted in the nose, provided concentrated firepower unprecedented in American fighters of that era. Unlike wing-mounted guns requiring convergence adjustments, the P-38's nose-mounted armament delivered all its firepower onto a single point. Japanese pilots who survived P-38 attacks consistently reported the terrifying intensity of its nose-mounted guns. The prototype XP-38 first flew on January 27, 1939, from March Field in California. On February 11th, Lieutenant Benjamin Kelsey attempted a transcontinental speed record, flying from California to New York in 7 hours 2 minutes. The flight ended in a crash landing at Mitchell Field due to carburetor icing, but it demonstrated the aircraft's remarkable speed. The damage was relatively minor, and the performance had been impressive enough to secure military orders. Production P-38 seconds began reaching operational units in mid-1941. Early models had teething problems. The original counter-rotating propellers were complex and troublesome, later changed to standard rotation. Compressibility issues at high speeds, where airflow over the wings approached the speed of sound, caused control problems. The cockpit heating was inadequate at high altitudes. Engine cooling required careful management. These were the inevitable issues of an advanced, complex design, and American engineers addressed them systematically through the P-38's numerous variants. By the time the Lightning reached the Pacific theater in quantity in 1942, it had evolved into a formidable weapon. The P-38F and P-38G variants that arrived in Australia in late 1942 incorporated improved engines, better superchargers, and increased fuel capacity. The P-38H introduced power-boosted ailerons to improve roll rate. The P-38J, entering service in mid-1943, featured improved intercoolers, increased fuel capacity, and better cockpit heating. Each variant represented accumulated combat experience translated into engineering improvements. What made the P-38 particularly devastating in the Pacific was its combination of range, speed, and firepower. Japanese fighters might have better maneuverability, but they could not outrun, outclimb, or outdive a Lightning. The P-38's twin engines provided not just power but redundancy. Numerous pilots returned safely on one engine after battle damage that would have been fatal in a single-engine fighter. The Lightning's ability to cruise at high speed for extended periods gave American pilots initiative. They could choose when and where to engage, attacking only when holding tactical advantage. The captured P-38 at Dobodura represented a G model, one of the earlier Pacific variants, but still embodying all the characteristics that made the Lightning so formidable. Once transported to Wewak and later to Japanese technical facilities in the Philippines, systematic examination began. Japanese engineers approached their task with thoroughness, born of desperation. They needed to understand not just what the Americans had built, but how they had built it, and whether Japanese industry could replicate or counter these capabilities. The examination began with overall dimensions and weight. The P-38 measured 52 feet long with a wingspan of 52 feet. Height to the top of the tail was 9 feet 10 inches. Empty weight was 12,800 pounds. Maximum takeoff weight exceeded 21,000 pounds. These numbers were staggering to engineers accustomed to Japanese fighters. The Zero weighed 3,750 pounds empty. Even Japan's newest fighters, like the Ki-84 Hayate, weighed only 5,900 pounds empty. The P-38 was more than 3 times heavier than a Zero. This weight carried implications beyond simple size. It meant structural strength sufficient to withstand combat stress and battle damage. It meant the ability to carry external ordnance. It meant armor protection for the pilot and critical systems. Most importantly, it meant the engines had to produce enormous power to achieve combat-effective performance while hauling such mass through the sky. Japanese engines struggled to produce reliable power even in lighter airframes. The thought of needing nearly 3,000 horsepower just to make a fighter competitive was sobering. The engines dominated initial assessment. Each boom housed an Allison V1710 engine, a 12-cylinder liquid-cooled design producing 1,425 horsepower at takeoff. Japanese engineers had encountered liquid-cooled inline engines before. The Kawasaki Ki-61 Heian used a license-built German engine, but the Allison represented American engineering philosophy in metallic form. Disassembly of one partially damaged engine revealed manufacturing quality that Japanese specialists found both impressive and demoralizing. The engine block was a massive aluminum casting of exceptional precision. Cylinder bores were perfectly round and smooth. The crankshaft, a forging of alloy steel, showed surface finish quality, indicating sophisticated machining equipment. Pistons, connecting rods, valve train components, all demonstrated manufacturing tolerances Japanese facilities struggled to achieve consistently. The supercharger system particularly impressed the technical team. Each engine featured a single-stage, single-speed supercharger, but its construction quality and efficiency exceeded Japanese expectations. The impeller was precisely balanced, the housing was smooth and well-finished. The entire assembly demonstrated mature understanding of fluid dynamics and manufacturing precision. Japanese attempts to develop effective superchargers had largely failed due to manufacturing limitations and insufficient understanding of high-speed aerodynamics. Perhaps most revealing was the engine's reliability characteristics. According to the P-38's maintenance logs, recovered with the aircraft, the engines had operated for over 100 hours since last overhaul. They were rated for 300 hours between major maintenance. Japanese engines, even when new, rarely achieved such reliability. The Nakajima Sakai engine powering the Zero was rated for just 150 hours total life, and many failed well before that due to manufacturing defects and material shortages. The propeller systems proved equally sophisticated. Hamilton Standard Hydromatic constant-speed propellers, each 11.5 feet in diameter, represented advanced aerodynamic design and hydraulic control systems. The propellers could adjust pitch automatically to maintain optimal engine RPM, regardless of flight and conditions. This reduced pilot workload and ensured engines always operated at peak efficiency. Japanese aircraft used either fixed-pitch or manually adjustable propellers. Automatic systems like those on the P-38 were beyond Japanese manufacturing capabilities. Examination of the airframe revealed construction methods that demonstrated American industrial sophistication. The central nacelle was an aluminum semi-monocoque structure, a load-bearing skin supported by internal frames. Riveting was precise and consistent. Each rivet was identical to the next, indicating automated or semi-automated assembly processes. Japanese aircraft construction increasingly relied on hand-fitting components, with resulting inconsistencies and quality variations. The twin booms were particularly impressive structures. Each boom was a complex assembly of aluminum bulkheads, stringers, and skin panels. The booms carried structural loads from the tail surfaces, housed the main landing gear, and provided a volume for fuel tanks and systems. Their construction required precise alignment and assembly. Any error would create asymmetric loads, leading to control problems or structural failure. That American factories could produce these complex assemblies consistently, in quantity, spoke to manufacturing capabilities Japanese industry could not match. The landing gear mechanism demonstrated engineering sophistication throughout. Main gear legs retracted rearward and upward into the booms, rotating 90 degrees during the retraction cycle. The mechanism was complex but precisely manufactured. All components were machined to close tolerances. The hydraulic system powering the gear used high-quality seals and precision-fitted cylinders. Japanese landing gear systems, even on modern aircraft, were simpler and less reliable. Many Japanese fighters still used tailwheel configurations rather than the nose-wheel tricycle arrangement the P-38 employed. The cockpit revealed a philosophy of pilot and support alien to Japanese thinking. American designers had created an environment optimized for long missions at high altitude. The seat was well padded and adjustable. The control column and rudder pedals were positioned for comfort during extended flight. Heating was provided, though it was inadequate by later standards. Most notably, the instrument panel presented comprehensive arrays of gauges and controls. Japanese engineers counted 37 instruments in the P-38's cockpit. Engine instruments for both engines, flight instruments, navigation instruments, radio controls, systems indicators. Each gauge was well made, with clear markings and smooth operation. The sheer quantity of information available to the pilot indicated a design philosophy emphasizing pilot awareness and decision-making support. Japanese fighters had far fewer instruments, reflecting both manufacturing limitations and a belief that pilots should focus on combat rather than system management. The armament installation provided clear evidence of American firepower philosophy. 4 Browning AN M2 50-caliber machine guns, mounted in the nose below the cockpit, each carried 300 rounds. Above them, a single Hispano M 120mm cannon carried 150 rounds. All weapons fired through the propeller arc, with perfect convergence at whatever range the gun sight was set for. No adjustments were needed. Every shot went where the pilot aimed. The ammunition feed systems demonstrated sophisticated engineering. Belt feeds for the machine guns were designed to function smoothly even under high-G maneuvering. The cannon's drum magazine was easily accessible for ground crew reloading. Spent cartridge cases were ejected through ports that prevented them from damaging the aircraft structure. Japanese armament installations were rarely this well integrated. Gun stoppages due to feed malfunctions plagued Japanese fighters throughout the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical examination extended to systems throughout the aircraft. The oxygen system provided compressed oxygen for high-altitude flight, with regulators to deliver appropriate flow at different altitudes. The radio installation included both command set for air-to-ground communication and liaison set for air-to-air. The quality of these radios, their reliability and clarity, exceeded anything in Japanese service. Japanese aircraft radios were notoriously unreliable, with many pilots simply removing them to save weight. The fuel system incorporated self-sealing tanks using multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss. This technology existed in concept in Japan, but implementation was inconsistent due to material shortages. Japanese pilots routinely flew in aircraft with unprotected fuel tanks, accepting catastrophic fire risk as unavoidable. The P-38's systematic protection of vulnerable systems reflected American willingness to accept weight and complexity for survivability. Flight control systems revealed further sophistication. Power-boosted ailerons on later P-38 variants used hydraulic assistance to reduce control forces at high speeds. Even the G model without such boosting had well-balanced controls. Cable runs were smoothly routed with proper fairleads and pulleys. Control surface hinges were precision bearings. Every aspect of the installation demonstrated attention to detail and manufacturing quality. But the most profound realizations came not from examining individual components, but from understanding the P-38 as an integrated system. American designers had created an aircraft where everything worked together. The powerful engines enabled heavy structure. The heavy structure provided survivability and weapon-carrying capacity. The sophisticated systems reduced pilot workload. The reliable components meant the aircraft could be maintained under field conditions. Every design decision reinforced every other, creating synergistic effects greater than the sum of individual parts. Japanese fighters, by contrast, were increasingly compromised designs. The pursuit of lightweight meant weak structure. Weak structure meant vulnerability. Unreliable engines meant frequent maintenance. Inadequate systems meant high pilot workload. These factors interacted negatively, creating aircraft that required exceptional pilot skill just to remain competitive against opponents who enjoyed technological advantages at every level. Captain Yamamoto's detailed technical report, completed in January 1944 and discovered in Philippine archives after the war, concluded with assessments that were professionally objective but strategically devastating. He noted the P-38's performance capabilities exceeded what Japanese intelligence had estimated. The engines produced more power than believed possible from their displacement. The structure was stronger and better manufactured than could be readily achieved in Japanese factories. The system's integration reflected engineering sophistication and manufacturing capacity that Japan simply did not possess. Most troubling was Yamamoto's analysis of what the P-38 revealed about American industrial capabilities. If Americans could design and mass-produce such complex aircraft, what else might they be developing? If their manufacturing quality was this consistently high across thousands of components in a single aircraft, what did that imply about production of ships, tanks, trucks, and weapons? The P-38 was not just an aircraft. It was evidence of industrial depth that Japan could not match. Flight testing of the captured P-38, assuming it occurred, would have provided additional sobering realizations. Japanese test pilots who flew captured Allied aircraft consistently reported similar findings. American fighters were fast, strong, and forgiving of pilot error. They could absorb battle damage and continue fighting. They had power to spare for climbing, accelerating, or escaping. These characteristics reflected engineering margins. American designers built aircraft with performance reserves, knowing combat would impose demands beyond normal operations. Japanese aircraft had no such margins. They were optimized for specific performance parameters, achieving excellence in those areas by sacrificing everything else. The Zero could outturn any Allied fighter because it sacrificed protection, firepower, and structural strength to achieve minimum weight. This worked when Japanese pilots were better trained and more experienced, but as pilot quality declined and Allied fighters improved, the Zero's limitations became fatal weaknesses. The examination of the P-38 occurred as Japan's strategic situation deteriorated rapidly. By late 1943, the the Central Pacific Offensive, had begun with the invasion of Tarawa. The island-hopping campaign would systematically eliminate Japanese strongpoints, each loss bringing American forces closer to Japan itself. In the Southwest Pacific, MacArthur's forces were advancing along the New Guinea coast, isolating and bypassing Japanese garrisons. At sea, American submarines were strangling Japanese merchant shipping, cutting off resources from conquered territories. Japanese aviation faced multiple crises simultaneously. Pilot losses in continuous combat were unsustainable. The Navy had lost many of its best pilots at Midway, and the attrition continued through the Solomon Islands campaign. The Army Air Force suffered similar losses in New Guinea and Burma. Training programs could not replace experienced pilots fast enough. New pilots arrived at combat units with minimal flight hours and were often shot down on their first missions. Aircraft production was constrained by material shortages and Allied bombing. Was increasingly scarce. High-quality steel for engine components was unavailable. Precision manufacturing equipment wore out and could not be replaced. Quality control suffered as production schedules demanded quantity over quality. Even when aircraft rolled off assembly lines, many had defects that would not become apparent until they failed in combat. Fuel shortages compounded every other problem. Japan's synthetic fuel production could not replace the petroleum imports from the Dutch East Indies that American submarines were cutting off. Training flights were reduced to conserve fuel. Combat units received limited allocations. Aircraft sat idle, not for lack of machines or pilots, but for lack of fuel. By mid-1944, fuel shortages would become critical, crippling Japanese aviation's ability to resist the American advance. The P-38 examination revealed all these weaknesses by providing concrete comparison to what American industry could produce. Every well-made component, every sophisticated system, every evidence of manufacturing quality highlighted Japanese inadequacies. The technical report's measured language could not hide their implications. Japan had entered a war against an opponent whose industrial capacity exceeded Japanese understanding. The gap was not small or easily closed. It represented decades of development, massive investments in infrastructure, and resources Japan simply did not possess and could not acquire. Japanese engineers and pilots who examined the P-38 understood these realities with painful clarity. Their reports, preserved in archives, show professional appreciation for American engineering achievements alongside recognition of what those achievements meant for Japan's prospects. These were not defeatist documents. They were objective assessments by competent professionals, confronting evidence that challenged their nation's propaganda about American weakness and decadence. The P-38's combat record in the Pacific substantiated everything the technical examination revealed. Lightnings achieved aerial victories at remarkable rates. The aircraft's speed and firepower made it deadly in boom and zoom attacks. Its range enabled escort missions protecting bombers deep into Japanese-held territory. Its versatility allowed adaptation to fighter-bomber missions, reconnaissance, and night fighting. The Lightning could do everything, and do it well. Major Richard Bong, America's highest-scoring ace, achieved 40 victories, flying P-38 seconds in the Southwest Pacific. Major Thomas Maguire scored 38 victories, also in Lightnings. Both men exploited the aircraft's advantages systematically, using speed and firepower to engage only when holding advantage. They could not outturn Japanese fighters, so they didn't try. They outflew them by playing to the Lightning's strengths. Perhaps the most dramatic demonstration of P-38 capabilities came on April 18, 1943, when 16 Lightnings from the 339th Fighter Squadron executed the mission to intercept Admiral Yamamoto Isoroku's transport. Flying from Henderson Field on Guadalcanal, the P-38 seconds covered over 430 miles of ocean navigation, intercepted Yamamoto's flight exactly on schedule, shot down his Betty bomber, and returned safely. The mission required precise navigation, perfect timing, and extended combat at the limit of fuel range. It showcased the Lightning's capabilities and American operational planning sophistication. Japanese response to the P-38 threat revealed institutional limitations beyond simply technical inferiority. Rather than acknowledging the Lightning's advantages and developing tactics to minimize them, Japanese doctrine continued emphasizing close combat where American aircraft held every advantage. Rather than focusing fighter production on designs that could match P-38 performance, Japanese industry continued building Zeros and other obsolescent types because retooling for new designs would temporarily reduce production numbers. Some Japanese aircraft offered competitive performance. The Ki-84 Hayate Frank, entering service in mid-1944, could match or exceed the P-38 inch's many performance parameters. But it arrived too late and in too few numbers. The J-2M Raiden Jack, designed as a high-altitude interceptor, had excellent climb rate and speed, but engine reliability problems plagued the type. The Ki-100, a Ki-61 with radial engine substitution, was arguably Japan's best fighter, but only 396 were built. The pattern was consistent. Japanese industry could design competitive aircraft. Individual examples sometimes achieved impressive performance, but translating designs into mass production with consistent quality proved impossible. Manufacturing limitations, material shortages, and increasing Allied air attacks on factories meant even good designs could not be produced in sufficient quantities with adequate reliability. The captured P-38 at Dobodura thus represented more than one aircraft. It exemplified everything Japan needed but lacked: manufacturing precision, material quality, engineering sophistication, system integration, production capacity. These were not problems that could be solved through determination or fighting spirit. They required industrial infrastructure Japan did not possess and, by 1943, could not develop before the war's outcome was decided. Technical intelligence from captured equipment continued throughout the war. Japanese forces recovered additional P-38 seconds, along with other American aircraft types. Each examination reinforced the same conclusions. American aviation technology was advancing faster than Japanese industry could respond. The gap was widening, not closing. By 1945, American aircraft like the P-51 Mustang and F-8F Bearcat represented such overwhelming advantages that even experienced Japanese pilots in modern aircraft had little chance of success. The psychological impact on Japanese pilots, who knew about the technical assessments, was significant. These men understood they were flying inferior aircraft against superior opponents. They were told that fighting spirit and Japanese martial virtue would overcome material disadvantages. But bullets and engineering realities cared nothing for spirit. Inferior aircraft flown by brave men still lost to superior aircraft flown by competent opponents. The knowledge that one's equipment was inadequate, that one's nation could not produce better, and that the enemy's advantages were increasing, created despair that no amount of ideological training could fully counter. Lieutenant Saburo Sakai, Japan's highest-scoring surviving ace, described the psychological burden in his post-war memoir. "We knew the American fighters were better. We knew their pilots were becoming more experienced. We knew our situation was hopeless. But we flew anyway, because that was our duty. Every mission felt like suicide. The bravest thing was not fighting, but taking off knowing you would probably never return." The story of Japanese examination of the captured P-38 Lightning is thus a story of dawning realization. Each component examined, each system analyzed, each performance parameter measured added to an inescapable conclusion. Japan had challenged an opponent whose technological and industrial superiority was so vast that defeat was inevitable. The P-38 was not unique, it was representative. If Americans could produce such aircraft in thousands, along with comparable excellence in every other military area, how could Japan, with its constrained resources and limited industrial base, possibly prevail? This realization came too late to change strategic decisions. By the time Japanese engineers understood the full magnitude of American capabilities, Japan was committed to a war it could not win. The examination of captured American equipment provided evidence for conclusions that should have informed decisions in 1941, before Pearl Harbor, when careful analysis might have counseled against initiating conflict. But by 1943, such analysis could only document the inevitability of defeat, not prevent it. The P-38 Lightning continued serving through war's end and beyond. Production ceased in 1945 after 10,037 aircraft had been manufactured. Lightnings served in Europe and the Mediterranean as well as the Pacific, though performance issues at extreme altitudes made it less effective against high-flying German aircraft. In the Pacific, where combat occurred at lower altitudes, the Lightning excelled throughout the war. Post-war, some P-38 seconds were converted for civilian use. Others served with foreign air forces. A few survive today in museums and flying condition, testament to their robust construction and historical significance. The distinctive twin-boom configuration remains instantly recognizable, an iconic silhouette from aviation's greatest conflict. For Japan, the encounter with the P-38 was part of a larger reckoning with technological reality during the American occupation. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war now worked with American occupation authorities to rebuild Japanese industry. Lessons learned from examining American technology, including the P-38, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in hard lessons learned during the war. Japanese engineers examining American equipment understood that excellence required not just good design, but consistent execution across entire production runs. It required proper materials, skilled workers, adequate tools, and effective quality control. These were systemic capabilities, not individual achievements. Building them required patient, persistent effort over years or decades. Post-war Japanese industrial recovery, supported by American aid and technology transfer, demonstrated what Japanese engineers and workers could achieve, given proper resources and stable conditions. The same nation that struggled to build reliable aircraft engines in 1944 became a global leader in automotive and electronics manufacturing by the 1970s. The transformation was dramatic but not mysterious. It reflected the application of lessons learned during wartime about what quality manufacturing required. The captured P-38 that Japanese pilots examined in late 1943 has long since vanished, likely scrapped during the chaotic post-war period. But the technical reports it generated survive in archives. They stand as evidence of a moment when one nation's technical specialists confronted another nation's capabilities and understood the full implications. The reports are remarkably candid, free from the hyperbole and propaganda that characterized much wartime Japanese documentation. They represent honest professional assessments by competent engineers, acknowledging truths their nation's leadership did not want to hear. In the final analysis, the story of Japanese examination of the P-38 Lightning is not primarily about aircraft technology. It is about the nature of industrial warfare, where victory depends not on courage or tactics alone, but on the ability to produce superior equipment in quantity with consistent quality. It is about the consequences of strategic decisions made without full understanding of opponent capabilities. It is about the price nations pay when ideology and propaganda prevent realistic assessment of military balance. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The P-38 Lightning, with its twin 1,425 horsepower engines, represented American aviation engineering at its finest. When Japanese pilots tested that captured example, they could not believe what American industry had achieved. But their disbelief changed nothing. The evidence was before them in aluminum and steel, testimony to capabilities that would help determine the war's outcome. In examining that aircraft, Japanese engineers confronted uncomfortable truth. Their nation had initiated war against an opponent whose industrial might they had fundamentally underestimated. The P-38 was proof they could measure, analyze, and document. But proof came too late to matter for the war's outcome, serving instead as epilogue to strategic decisions that sealed Japan's fate years before. The attempt to make the captured P-38 airworthy revealed further dimensions of the technological chasm. Japanese maintenance crews, working at facilities in the Philippines where the aircraft had been transported for detailed study, faced immediate challenges. The Lightning's complexity exceeded anything in their experience. Standard Japanese maintenance procedures, developed for simpler single-engine fighters, proved inadequate for an aircraft with twin engines, complex hydraulic systems, and sophisticated electrical networks. First Lieutenant Hiroshi Nakamura, a maintenance officer assigned to the evaluation team, documented the difficulties in reports that survived the war. The technical manual recovered with the aircraft contains over 400 pages of maintenance procedures, troubleshooting guides, and systems diagrams. Our most complex fighter, the Ki-61, has a manual of 120 pages. The P-38's hydraulic system alone requires more specialized knowledge than our entire aircraft. We lack proper tools, replacement parts, and in many cases, the fundamental understanding of how American systems are designed to function. The engines presented particular challenges. Both Allison V-1710s had suffered damage during the forced landing and subsequent recovery operations. One engine had taken combat damage, the other had ingested debris during the crash. Japanese engineers attempted repairs using whatever materials were available. Precision bearings were impossible to obtain. Gaskets had to be fabricated from inappropriate materials. Spark plugs of the correct type did not exist in Japanese inventory. Even basic items like engine oil of proper specification were unavailable. After 6 weeks of intensive work, one engine was coaxed into running. The sound it made, a deep, powerful rumble, entirely different from the high-pitched scream of Japanese radial engines, impressed everyone present. Chief Warrant Officer Kenji Ishikawa, who supervised the engine work, wrote to a colleague at Nakajima Aircraft Company. When the Allison fired and settled into smooth idle, producing more power at idle than many of our engines produce at full throttle, the implications were sobering. This is what 12 cylinders, liquid cooling, and American precision manufacturing achieve. We have nothing comparable. Even if we possessed complete technical drawings and unlimited resources, I doubt our factories could replicate this engine's quality and reliability. Flight testing, if it occurred, was limited and fraught with difficulty. Japanese test pilots familiar with American aircraft types were few. Those with twin-engine experience were fewer still. The P-38's tricycle landing gear alone required techniques unfamiliar to pilots trained on conventional tail-wheel aircraft. The nose-wheel steering, the tendency to porpoise during landing if technique was incorrect, the need to manage 2 engines simultaneously during takeoff and landing, all represented challenges beyond most Japanese pilots' experience. Squadron leader Masahiko Takahashi, a test pilot who had evaluated several captured Allied aircraft, was reportedly selected to attempt flights in the P-38. His handwritten notes, discovered decades later among family papers, provide fragmentary glimpses of the experience. The cockpit is spacious compared to our fighters. Visibility is excellent in most directions, though the nose blocks forward view during ground operations. The control forces are heavier than expected. American pilots must be physically stronger, or perhaps their training emphasizes different techniques. The twin throttles require coordination. Advancing them unevenly creates asymmetric thrust that must be corrected with rudder. Whether Takahashi actually flew the P-38 remains uncertain. Some accounts suggest a brief test flight occurred. Others indicate that damage and parts shortages prevented restoration to fully airworthy condition. What is certain is that even ground runs and taxi tests provided valuable information about the aircraft's characteristics. The acceleration during takeoff run, the control response, the engine power, all could be evaluated even without flight. Comparative analysis between the P-38 and Japanese fighters revealed disparities across every performance category. Japanese technical staff prepared detailed comparison charts, some of which survived in captured documents. The numbers told a story of comprehensive American superiority. Maximum speed: P-38 Lightning, 414 miles per hour at 25,000 feet. Mitsubishi A6 M50, 351 miles per hour at 19,000 feet. Nakajima Ki-84 Hayate, 392 miles per hour at 20,000 feet. Climb rate: P-38 reached 20,000 feet in 7 minutes. The Zero required 7.5 minutes. The Ki-84, Japan's best-performing production fighter, required 6.5 minutes. Even Japan's newest designs could barely match a P-38 variant introduced in 1942. Range: P-38 combat radius exceeded 450 miles with drop tanks. Ferry range approached 2,000 miles. The Zero's remarkable range of over 1,500 miles came at the cost of protection, structure, and firepower. American designers achieved comparable range without such compromises. Service ceiling: P-38 operated effectively above 40,000 feet. Japanese fighters struggled above 30,000 feet. Engines lost power. Pilots suffered from inadequate oxygen systems and poor cockpit heating. The Americans had solved high-altitude operational problems Japanese aviation never adequately addressed. Firepower: P-38's concentrated nose armament of 450 caliber machine guns and one 20mm cannon could destroy targets with brief firing passes. Japanese fighters typically carried 2 rifle-caliber machine guns and 2 20mm cannons, but wing mounting required convergence adjustment and reduced effective range. Structural strength: the P-38 could dive at speeds exceeding 450 miles per hour without structural failure. Japanese fighters experienced control issues, structural damage, or complete breakup if attempting such speeds. Combat maneuvers that American pilots executed routinely would overstress Japanese airframes beyond design limits. Protection: P-38 pilots sat behind armor plate with bulletproof glass. Fuel tanks were self-sealing. Critical systems had redundancy. Japanese fighters sacrificed protection for weight savings. A single well-placed burst could destroy what took months to build and years to properly train a pilot to fly. The psychological impact of these comparisons on Japanese aviation personnel varied. Some, particularly younger officers and technicians, accepted the evidence and advocated for radical changes in doctrine and production priorities. Others, especially senior officers invested in existing systems, rejected conclusions that contradicted years of professional beliefs. The institutional response fell somewhere between acknowledging problems while remaining constrained by practical realities of limited resources and production capacity. Colonel Takeo Shibata, commanding the 4th Air Army's fighter units in New Guinea, received detailed briefings on the P-38 examination findings. His response, recorded in operational orders issued in February 1944, reflected clear-eyed realism. Intelligence analysis confirms American P-38 Lightning possesses performance advantages across all categories. Our fighters cannot match its speed, climb, or firepower. Doctrine is revised accordingly. Engagement with P-38 is authorized only when tactical advantage is overwhelming. Preferred targets remain bombers. Fighter versus fighter combat should be avoided when possible. Survival of experienced pilots takes priority over inflated victory claims. This represented significant departure from earlier Japanese tactical doctrine, which emphasized aggressive engagement regardless of odds. But Shibata understood what many senior officers refused to accept. Japan's dwindling pilot pool could not be squandered in hopeless battles against superior equipment. Better to preserve forces, attack when advantage existed, and husband resources for battles where they might matter. It was defensive thinking, an admission of inferiority, but it was realistic. Not all commanders shared this pragmatism. Some insisted fighting spirit could overcome material disadvantages. These officers ordered aggressive tactics that sent inadequately trained pilots in obsolescent aircraft against American formations. The results were predictable. Japanese loss rates climbed while victory claims, always inflated, bore increasingly less resemblance to reality. Units were destroyed and reconstituted multiple times, each iteration weaker than the last as experienced survivors became rarer. The human cost of technological inferiority appears starkly in unit records. The 68th Sentai, flying Ki-43 Hayabusa Oscars in New Guinea, engaged P-38 seconds on 23 separate occasions between January and May 1944. They claimed 19 P-38 seconds destroyed. Actual American losses in those engagements were 3. Japanese losses were 62 aircraft with 41 pilots killed. Similar patterns repeated across every combat theatre. Japanese pilots fought bravely, often skillfully, but courage could not overcome a 400-mile-per-hour speed disadvantage or the ability to absorb battle damage that would destroy their aircraft. Individual testimonies from Japanese pilots who survived encounters with P-38 seconds provide human perspective on these statistics. Warrant Officer Yoshio Fukui, flying Ki-61 Hyans with the 68th Sentai, described an engagement in his diary. Escorting our bombers to Hollandia when P-38 seconds bounced us from above. They came so fast we barely saw them before they were through our formation. My squadron leader exploded. I saw hits on at least 3 other aircraft. I broke hard left, blacked out, momentarily from G-forces, recovered to find myself alone. The P-38 seconds had already climbed back to altitude. They did not pursue. They did not need to. They had destroyed half our formation in seconds, and we never touched them. This pattern of slashing high-speed attacks, exploiting energy advantages, and refusing to engage in turning combat played to every P-38 strength while negating Japanese advantages. American pilots received extensive training in these tactics. Fighter training emphasized understanding one's aircraft capabilities, recognizing opponents' strengths and weaknesses, and engaging only when holding advantage. The training also stressed teamwork. American pilots fought as mutually supporting pairs and 4-plane divisions. Japanese training, increasingly abbreviated as the war progressed, produced pilots with basic flying skills but inadequate tactical training and no experience working as coordinated teams. The P-38's effectiveness extended beyond air combat. Its range enabled fighter sweeps deep into Japanese-held territory, attacking airfields, destroying aircraft on the ground, and disrupting logistics. The twin engines provided reliability for extended overwater navigation. Pilots who would have been lost in single-engine fighters returned safely after engine failures. The aircraft's versatility allowed rapid role changes. A morning fighter sweep could be followed by afternoon ground attack missions. Drop tanks extended range. Bombs and rockets provided ground attack capability. Reconnaissance variants carried cameras. Night fighter versions mounted radar. This versatility reflected American production philosophy. Rather than developing specialized aircraft for every role, American designers created adaptable platforms capable of multiple missions. The same basic P-38 airframe served as day fighter, night fighter, reconnaissance aircraft, and fighter bomber. Production remained concentrated while operational flexibility multiplied. Japanese, Aviation by contrast, developed specialized aircraft for specific roles. This fragmented production created logistics complexity and reduced overall effectiveness. The examination of the captured P-38 concluded in mid-1944 as American advances forced evacuation of technical facilities in the Philippines. Final report summarized findings and offered recommendations. The recommendations section makes particularly interesting reading. Japanese engineers understood what needed to change. They lacked authority and resources to implement changes. Immediate priorities should include development of engines producing minimum 1,500 horsepower, with reliability matching American standards. Airframe design must emphasize structural strength and pilot protection without excessive weight penalties. Production quality control must improve dramatically. Specialized tools and precision manufacturing equipment must be obtained or developed. extensive revision, emphasizing tactical employment and energy management. Every recommendation was sound. None would be implemented effectively before war's end. Engine development programs existed but produced unreliable results. Airframe improvements were incorporated in new designs, but production remained constrained. Quality control suffered as factories operated under increasing Allied air attacks. Precision manufacturing equipment could not be obtained. Germany, the potential source, faced its own crises and had little to spare. Pilot training programs nominally adopted new curricula but lacked fuel and aircraft for proper instruction. The captured P-38 itself probably did not survive the war. American forces, advancing through the Philippines in 1945, found numerous destroyed Japanese aircraft, including some identifiable as captured Allied types. Whether the specific aircraft examined at such length was among them remains unknown. More likely it was destroyed by Japanese forces during retreats to prevent recapture. Its fate matters less than its impact on those who examined it. For Japanese aviation personnel, the P-38 represented confirmation of what many had suspected. Their nation had challenged an opponent whose industrial capabilities exceeded Japanese understanding. Every rivet, every precisely machined component, every sophisticated system testified to manufacturing capacity and engineering sophistication Japan could not match. The realization came too late for strategic redirection, but early enough that those involved understood they were witnessing their nation's defeat, unfolding in technological superiority they could measure but not counter. The lessons learned examining the P-38 influenced post-war Japanese thinking about technology and industry. Many engineers and technical specialists who studied captured American equipment survived the war and contributed to Japan's post-war reconstruction. They understood that quality manufacturing required not just skilled workers but proper tools, adequate materials, effective processes, and institutional commitment to excellence. These insights, combined with American technical assistance during occupation, helped transform Japan into a manufacturing powerhouse within a generation. The P-38 Lightning itself became less significant as the war progressed. Newer American fighters like the P-47 Thunderbolt and P-51 Mustang offered comparable or better performance. The Lightning's complex maintenance requirements and cold weather operational issues limited its effectiveness in Europe, but in the Pacific, where its range and twin-engine reliability mattered most, the P-38 remained formidable through war's end. The last P-38 combat loss in the Pacific occurred on August 14, 1945, the day before Japan's surrender. Looking back across 8 decades, the story of Japanese examination of the captured P-38 Lightning reveals truths about technological competition, industrial warfare, and the consequences of miscalculation. Japan entered war believing spirit and skill could overcome material disadvantages. The P-38, with its twin engines producing combined output exceeding anything in Japanese service, proved that belief catastrophically wrong. No amount of courage or fighting spirit could change the fact that American industry could produce such aircraft in thousands while maintaining quality standards Japanese factories could not match even in small quantities. That realization, documented in technical reports written by competent professionals confronting uncomfortable evidence, stands as epitaph for Japan's failed challenge to American industrial supremacy.